Thank you for joining Once Changing the World. I'm your host, Eddie Avil, and we have a wonderful co-host today, Mr. Jeremy Dalton. And our guest for today is Giacomo Valle, an assistant professor at Chalmers University of Technology. He leads the Neural Bionics Lab. He and his team is engineering the future of prosthetics, building bi-directional brain-computer interfaces that don't just decode thought, but send touch back to the brain, from restoring patented tactile sensations through intracortical microstimulation to setting the ethical technical standards for implantable neural prostheses. Giacomo is redefining what it means to merge biology with technology. This is lab-to-market translation at its boldest. Mechatronics, computational modeling, and medical devices designed to accelerate human capability. So, Giacomo, really appreciate you taking time and being part of the podcast. Brain is something, I've been so fascinated with, because that's one organ in our body which has the capability to create war, create love, create innovation, and so on and so forth. But still, we know very little of it. It's almost like AI, artificial intelligence, which we call it like a black box, rightfully so, because we don't really understand the underpinnings of how the model works. The same goes with the brain, though there's been lots of working, in the space of, brain-computer interfaces, EEG, fMRI, and there's these organoids and so on and so forth. But we still connectomics, but we still do not completely understand the brain. So, maybe it'll be great if you could give us an overview of the brain and also a brain-computer interface, and specifically what you're working on, like a bi-directional brain-computer interface. So the brain, bi-directional brain-computer interface, and how does it work?
Yeah, absolutely. So first of all, thank you very much for this invitation. It's a pleasure to tell you better what is exactly this field and what are like the challenges also connected to that. So as you mentioned, the human brain is, in my opinion, one of the most complex thing in the known universe. We have this machine in our head that with 80 billions of neurons with trillions of synapses connected. It's very complex and is evolved over thousands of years. So evolution has like this, and in particular, thanks to the structure of the brain and the evolution of the brain, we are intelligent. Our intelligence is remarkable, and actually, this is very fascinating. It is, for example, what attracted me in this field of brain-computer interface, to try to understand better our brain, but also on the other hand, the problem is that when something is happening inside our brain, like in terms of a disease or a neurological condition, then this becomes really difficult to tackle. Since we don't know much about that, then it's difficult to treat or intervene, with a drug or with the technology. And I think it's fascinating also to think about conditions where there are people maybe that are with a gunshot in the head, or like burn with water in part of the head. And there are some case studies showing like people with less than half of the brain, and then they discovered that in an fMRI, and then they are pretty normal people, like from outside. So this is like other evidence of the fact that we don't know. There are many things that we don't know. How the brain also is restructured, is very plastic, so can adapt very easily to changes on the environment. So that, as we said, like the neurological condition, indeed, for this reason, most of the time are some like untreatable, or like there are intervention where after the phase where the clinician, the doctor, can save your life. For example, after a stroke or after a traumatic brain injury, there is this phase. But then after this phase, there is no much to do recover. No, your condition stabilize, and then people with a stroke, for example, they have limited mobility, they have limited maybe capability to speak and interact. And the same is for people with spinal cord injury. So where the injury is not even in the brain itself, but maybe in another part of the nervous system, because our nervous system is composed also by our spinal cord. So that is the way in which the brain is connected to our muscles, our organs, and we have all the peripheral nervous system with the nerves that are going in our body. And so even if the lesion is there, then again is an intervention. There is an acute intervention, some rehabilitation, but then the condition of a person with a spinal cord injury and with paralysis is without really a cure, without really like a solution, no? So in the recent years, not even so recent, but I think this field started also with the pioneeristic work from Galvani and also people before that. They started to understand that the nervous system, including the brain, is communicating and transferring information via electrical signals. So very similar to our computers or like our electric circuits. This is like bioelectricity. So and this little like electrical signal as traveling and are commanding information to move our body, to control our organs, and also inside our brain to think, to speak, and all the things that we do. So they started to develop tools to interact with the brain via bioelectricity, via electrical interaction. So that means that in principle, the idea was if you have a sensor that in this field is called mostly electrodes. If you have a sensor, you can place a sensor in a part of the nervous system, and you can record this electrical signal. And maybe from these recordings, you can understand something about what is happening in your nervous system. But you can also, in principle, stimulate the cells, so inject electrical signal, and via this stimulation you can interact, modulate, and modify the function of the nervous system. So and this is the principle at the end, at the base of the brain-computer interface, and in particular with the bidirectional brain-computer interface. So what is possible is to have a device that can interface with the brain at different level, but in general, this technology is for the cortical region, for the brain, and you can place this technology close as possible. This is what our vision, but you can also place outside, as you mentioned before. The EEG is placed outside of the skull, and you can record this electrical signal, use algorithms and computer-based algorithms that are to extract information, to try to understand from this electrical signal what is happening, and maybe use that to provide some support to people with limited mobility or with limited capability to interact. And on the other hand, you can use the same technology to stimulate and to provide back some feedback.
The bidirectional aspect is really interesting to me. So I understand the idea of sending a signal from the brain to a limb or a sensor, but the other way round has gotten me curious. So if you had a sensor, let's say someone was missing an arm, for example, what would be the use case of sending a signal from the sensor back to the brain? Can you try and explain that to me in layperson terms, please?
Exactly. So here there is so what is important is to understand that when we try to support and help the people with neurological conditions, like from spinal cord injury, or like can be an amputation with also we develop robotic limbs that can support these people. We are trying to be inspired by the natural system, our biological system, how we interact with the external environment. And actually there is when you want to provide some support in terms of motor function and movements. So the idea is for a person with spinal cord injury, for example, is to give the opportunity to control a prosthetic limb that you can imagine aside of a wheelchair. And then the person can think about moving his or her own arm, and then we can understand that from our brain-computer interface and command this robotic hand to interact and maybe reach some object on the table or catch other things around the person. But what is happening is that our we are very dexterous. We are very able to very fine movements when we interact with the environment, right? And also, this is another flagship of humans. So our hand is very dexterous and very specific. But this is due not only to the motor and the movement part, but because we have a very fine and detailed sense of touch. So when we interact with object, we can extract information. We have kind of biological sensors in our hand. And when we interact with an object, we can immediately understand the shape of the object, the texture of the object, if a soft object is a live object or not, in very few milliseconds. And this is make us, this signal that is going to our brain when we interact with the object, make us very able to adjust our movement accordingly to what we are feeling. And so there is a very tight connection between our sensory system and our motor system. So if you know that this thing, then when you replace with a prosthetic hand, for example, what is missing is this sense of touch, no? Because the subject can control the prosthesis, but cannot feel any sensation from the object that they are touching. So, for example, they cannot regulate force. So if you want a delicate grasp like an egg or something, you will break the egg because you will not feel the force that you are applying. So the idea here that we introduced was to try to send back information, like close the loop, we say, send back sensory information, sensory feedback, and the sensory feedback will allow the user to actually use the bionic hand or the robotic hand more efficiently because of this sensory information.
How cool is that? In the beginning of the conversation, you said the brain is like a machine, because it's pretty much, it does like that, electrical and chemical signals which is firing, 80 billion neurons, 100 synapses, the way they fire and wire, it brings about all the senses: sight, sound, touch, smell, taste. And you spoke about the diseases, if we are able to possibly understand the brain, there are so many neurological disorders that we could kind of reverse. Now, both of us, Jeremy and I, we are both deeply vested in the XR space for the longest time. And with virtual reality, we have pretty much cracked two modalities, which is the sight and sound. Sight and sound, we do it pretty well. Sight, we can do photorealistic content. You hardly will be able to distinguish between what is real and what is virtual. And so is the audio. We can, emulate sound as like we hear, which we call it ambisonic or spatial sound. Now, these other three modalities, the touch, smell, and taste, is still far away, though there are people who are kind of tinkering around with haptic feedback suits. We've got these haptic feedback gloves and, body suits and shoes, which gives you like a rudimentary vibration, that the same feeling that you get on your phone, But there are companies like there's Afference Inc., who's trying to possibly, do a bi-directional interface where they're trying to, there's like a micro stimulation where they power some electric currents to kind of give you that basic kind of a feeling. Now, that the breakthrough in the lab was, you kind of enabled with Cortical Bionics Research Group, partnering with them. There was this artificial touch which you enabled for your patient. Can you elaborate on that? When you say that, how does it work? I mean, how do you understand that a certain part of the brain gives you the feeling of touch? And you mentioned force. How do you kind of understand that, and how did you make that happen?
Yes, no, exactly. It's very similar, the concept to what Afference Inc. is doing, like at the peripheral level, but here we are at the central level in this sense. So when there is an amputation, for example, or even like in a healthy and able body person, the concept there is to have like these sensors, or we can call like these electrodes, implanted in the nerves and stimulate and interact with the nerves. So at the peripheral level, you can send information to the brain, and actually because the nerves are these highways that starts from our extremities and then goes up to the brain, and then the brain elaborates the signal that is captured by our nerves. So if you interact with the nerves, you can evoke sensation, for example, for a prosthetic device for a person with an amputation. But even if you think that if you are in virtual reality, exactly this haptic feedback, you see things in virtual reality, and if you interact with this object in virtual reality, you can stimulate the nerve that are evoking sensation on the hand, and then when you stimulate, you will feel this object in your own hand. But here, actually, it's unfortunately not possible, because what we develop technology with people with paralysis, where the lesion is above, like it's at the cervical level, so at the neck level normally, and there are people with it's called quadriplegia, so is a paralysis affecting the four limbs. So people are not feeling and cannot move from the neck down. So you cannot, in that case, you cannot interface with the peripheral nervous system, because any signal that you send up then will be interrupted by the lesion. So the idea here is that, okay, the periphery is not available. What we can do for these people? But actually, what is important is that in case of a spinal cord injury, exactly, you lose the connection of your brain with the body, but actually your brain is healthy. Your brain is still functioning as an able body brain. So what happened is that the cool thing about our brain is also the fact that it's organized in areas. So there are specific areas that are functioning and are processing and are responsible for specific things. In our case, what we were searching for is the area related to our motor movements. So in this case is the motor cortex, and then you have the yin and yang. So you have the sensory cortex, the somatosensory cortex, that is next to that in your brain. So you have your vision is processed more posterior, then your frontal areas are more for cognitive function, and you have the parietal areas that are more for sensory motor functions. So, and this is clearly visible also from if you are like in a fMRI, so in a magnetic resonant imaging, and you think about moving your hand, this part of the brain will light up. If you think about moving your arm or your hand contralaterally to your movement, so you know that there is this cross, and then if I touch your hand, then there will be the activation on the area next to that. So thanks to this clear separation in the brain, and this is called somatotopy. Thanks to this organization, we can know exactly where I have to place our technology to extract or interact with the nervous system at the level of sensory motor control. So what we do is to place the participant and the patient in a MRI imaging, and we ask the participant to imagine to move the arm, imagine to feel, and these areas will appear active as is an able body brain, because at the end, what happened in the injury is that the messages are going, but then are interrupted, that cannot go and activate the movement, the muscles and the joint to move. So when we know where to place the electrodes, that is can be slightly different in every participant, because the structure of our brain is also different between us, but more or less in the same region. We implant these particular electrodes. So these are electrodes similar, if you want, similar to the Neuralink device also developed by Elon Musk, where actually you have these tiny electrodes, and we implant hundreds of that in these areas. So in the areas of the arm, related to the hand movements, and also related to the sensation. So what happened there after the recovery, now we are able to record the electrical signal when the subject is imagining or attempting to move the arm and the hand. And with the other electrode in the somatosensory cortex, we can electrically stimulate this part of the brain, that is the part of the brain that is receiving information from the hand and processing this information, make us understand and perceive sensation on our hand. So if you stimulate those neurons that are there, you will actually perceive a sensation on your hand, because these are the neurons that are processing this information. So thanks to this, we can, every time that the prosthetic hand, the robotic hand will touch an object, and we have sensors on the robotic hand, we can stimulate the part of the brain related to the index finger, to the middle finger, and things like that, and then give the impression, the feeling of the user to that this object is in his or her own hand. And this will allow the user to use much better the prosthetic hand. But also, touch is involved in many other things. Like touch is there is also the affective component. We use our the sense of touch to interact with others, we hug other people. We feel connection through touch. So this is also making like the robotic hand and the prosthetic hand more as part of yourself. It's not just an external object, but it's actually you feel sensation from that. So you feel that as part of yourself.
So I'm really glad that you mentioned the Neuralink, Giacomo, and I'm curious about your view on it, because from a marketing perspective, Neuralink has done a fantastic job. We hear about Neuralink everywhere all over the world. People are fascinated by it. I feel like as an outsider to the field, Neuralink has kind of opened up the public's mind to the possibilities of what you can do with devices like this. But the question I have is, how special of a product is Neuralink? Is there something truly unique about it? Or is it very much a matter of a lot of marketing spend happening, and that's what's driving all of the interest in that particular device in the wider field of neuroprosthetics?
Yeah. No, this is absolutely a good question. So the concept per se is not new in general. No, the concept of a brain-computer interface using an invasive or implantable device connected directly to this region of the brain, and use this device to stimulate and record, starting from non-human primates and also in other animals, started like many years before Neuralink. The first participant implanted with the brain-computer interface of this kind was in 2006. Actually, the study was published in 2006, so the implant was even like some years before, and they proved that implanting, this was done by BrainGate in the US. They implanted these electrodes that we still use in some trial, the same type of electrodes, and implanted in the motor cortex, and the subject was imagining to control a mouse. Let's imagine like this. So if you imagine to move a mouse to control a cursor on the screen, your part of the brain related to the arm and the hand will be activated. For every movement that we do, there is a specific activation. The direction and velocity of this movement is encoded in this activation. And so if you have a smart algorithm, you are able to understand if the subject wants to move the cursor up, the cursor's left or right. So thanks to this brain-computer interface, there was a demonstration of this this person with paralysis able to control the cursor on the screen just by thinking about moving the cursor. And that was already like 20 years ago. So the point here is that what is very remarkable, the work of Neuralink, is like, in my opinion, like or two or three things. Like the first thing is that so with years and the evolution of technology to interface the brain, I think there are now more, with the advancement of materials, advancement of the microfabrication, the fact that we can do very, very small electronics, very, very small electrodes. So this allow to unlock really like another level of brain-computer interfacing, because what they propose is to have thousands of electrodes, like thousands of channels that we can use and read. Because one thing that we said at the beginning, so our brain has billions of neurons, no? And if you place one electrode only, you will be able to record the activity of few neurons that are those that are around your electrode, but all the others are not recordable. In principle, like there is a problem of bandwidth between our capability to record and speak and with these neurons. And so even if we have hundreds of electrodes, we are still undersampling the space a lot, because there are millions of neurons around your electrode. So the possibility to scale and have hundreds of thousands of electrodes is incredibly fascinating and can really unlock a lot of power. So they propose like to have really thousands of electrodes available. They also they also developed something completely wireless. That is another thing that was pretty new, because one of the concern of having like a brain implant, at least before, was also the fact to have like a connector coming out, similar to science fiction movie like Matrix. I don't know, you have a connector and then you have a cable connected to that, and then this is able to stream information or like to send information. But here, for example, what they developed is a solution that is actually wireless. And the third thing that it was pretty remarkable technologically is the robot for implantation. So one of the things is that if you implant 1,000 of electrodes, of course, in your brain you have the neurons, but you have also vessels, veins, and arteries that are bringing blood, to the part of the brain. And when you implant, you want to avoid to break and to damage this vessel, that are bringing the nutrients and the food to the cell. So they developed this robot that is able to implant automatically these electrodes, these wires, very small, and avoiding the veins and the vessels. So in my opinion, like this is the opinion also of the field, that in general, technologically, they did an incredible work. And in particular, they managed in not a lot of years to catch what the research was able to prove in many years. Of course, they built on the shoulder of the giants of the science and the research, and many of researchers that were before scientists are now working with Neuralink. And of course, this is also connected with an availability of funding that is unprecedented, I think, in the field at least. So I think they have the vision to see that this is a possibility and something that can really revolutionize the way in which we interact with technology and the possibility to have a bidirectional connection with the brain. And they develop a very smart technology, and they hire good people, and they have a lot of money. Still, in my opinion, like of course, is a company, so there are two things that maybe are questionable. One is what they propose and they aim to do. That as maybe a scientist in the field, I feel sometimes very ambitious and maybe not possible at this time with the algorithms, with the knowledge that we have of our brain. So there is still things to do. We cannot read minds. This is not possible. But and on the other hand, it's a sensible topic, I feel. Brain data, the possibility to interact with the brain. So I'm not super comfortable maybe to think about a company owning like brain data of the participants. So we have, in particular in Europe, but in science in general, very strict regulation about data privacy of the patients, how to deal with the data, and how you share the data and the knowledge with the rest. And this is maybe for a private company, but this is not only for Neuralink. In general, when these type of things are private, this is maybe less regulated compared to the public sector.
Did you interesting, as at the same time it could get scary very, very fast. And I think we are at the cusp of maybe miniaturizing technology, and maybe these BCI arrays maybe will get more and more smaller. And there's companies who are like working with different approaches. There's Science Corporation, the ex-CTO of Neuralink. He's looking at creating a biohybrid BCI, which kind of merges into your brain. So it's not these micro electrodes. Then there's Merge, which is kind of just partnered with Open BCI, and they're looking at ultrasound. How cool is that? There's so many others. I was just kind of speaking to somebody who's working in the field of Alzheimer's, and there's a team in China who's kind of figured out to reverse Alzheimer's, not in humans, but in primates, which is monkeys, only through the power of sound, which is 40 hertz sound. So there is so many things out there which we have still not figured out. And hopefully, maybe artificial intelligence will maybe help us expand on knowledge and maybe bring these things, which is already there, and find ways to kind of, maybe integrate this into this field of healthcare. Now, the brain, 80 billion neurons, 100 trillion synapses, the way they fire and wire brings up all the senses. How much do we understand the neural correlates? You're looking at like the touch and feel. How much do we understand? And is there like a language going on? Because this electric firings and wirings, I'm sure eventually we should be able to kind of understand that. And then maybe, we'll have like that complete closed loop, two-way bidirectional BCI. So the question is, do you think that artificial intelligence maybe might be able to make sense of this messy data of these electrical firing and wiring, and give us like a proper language, that this is the language eventually then which we'll be able to feed it into like a model and create a bidirectional BCI?
Yeah, this is an excellent point. It's absolutely like the possibility to use AI based algorithms to decode about our brain. If we see that in like there are two different parts, in my opinion. One part is the use of BCI to provide like assistance and support for patients with neurological condition. So actually, in that case, what you need is a technology that is functional, is able to provide benefit, robust, that can be used at home and stuff like that. So in that case, for example, AI helps a lot because with the improvement of the algorithms, it's now possible to decode from this when we stream thousands of channels that are are all these neurons firing at different time at a different amplitude. Like there is a lot of going on. This code is very, very complex. If you feed that in a neural network, the neural network can gives for do the job for you and tells you, okay, this pattern of activity is related to this action, this other pattern, the subject wants to do this other action. So we can use AI-based algorithms to create decoders, are called, so decoding algorithms that can be used to control a robotic arm, to control a computer cursor, to convert brain signal in voice and text. There are also BCI for speech restoration in people with ALS. And in that case, I feel AI, instead of basic algorithms to understand, okay, this neuron is firing, so that means here. So if expand a lot the performance and the capability of these devices. On the other hand, there is the other aspect of this technology that once you have, so this technology are also, as you said, are also allow us to study the brain in a unique way, because now that we have brain implants in humans implanted with very high resolution, with hundreds or thousands of channels of information, we are now understanding something that before was not possible, because most of some of the studies or most of the studies about the brain are done or with in neurosurgical intervention, or you know that this area is functional of your brain is involved in this, because if you have an injury on that area, you will lose that capability. So they understood that, okay, this area is involved in this area is involved in that. Or also in MRI, if you put a person in a scanner and you ask the subject to do things, you will see some specific area activated, and so you can understand more about the function of the brain. But now that we have this close window, super intimate connection with the brain, we can now see the neural code of specific things. So we are understanding a lot now about the brain itself, thanks to this technology. With that said, so if you use AI in that part, sometimes it will be difficult to interpret and understand actually what is happening, or maybe approach it more knowledge based instead of data driven, as AI will help us to understand better the rules and the relationship of the neural code with the behavior, for example, of the neural code with the sensation. But still, it's an incredible tool that, when connected with the neural data, can really. It's adopted. AI-based decoding algorithms are using and are really outperforming conventional approaches. But I feel that still, for understanding the brain, we need knowledge-based approach, where actually we can understand that, have more an explanation of what is happening. That sometimes with AI is more like a black box, and we know the output, but we don't know how.
So the connection or the convergence of emerging technologies is really interesting. And I think the World Economic Forum raised this as a point last year in a report which specifically talked about the value of multiple technologies coming together. And I think the point you're talking about is really interesting, because it starts to bring together artificial intelligence and brain-computer interfaces and the new possibilities that get created as a result of putting those technologies together. Yesterday, I spoke with an Australian company, a company called Vertetic, and they are in this field somewhat. They have a device which is a sensor that attaches to a stump of a limb where that limb is missing. And the idea is you put on a virtual reality headset and you practice operating a prosthetic limb in virtual reality before you get the prosthetic itself. And it's a way of training that that usage of the prosthetic so that you are best able to use it when it arrives. So I think there are some really interesting examples of convergence of emerging tech, AI and BCI, VR, BCI. Have you seen any other sort of convergences of emerging technologies that you find personally interesting, or even if it's a theoretical, what could we do in the future if we combine these technologies together? I'd love to get your thoughts on where we might go with these combinations.
Yeah, no, exactly. Like this is really like a multidisciplinary field. No, in particular, like when there is technology connected also with the human, um with the biological part, is making everything more complex, of course, but is also mixing a lot the knowledge of the team involved in working in this research is normally very, very diverse. Like we have like, of course, clinician and the surgeons expert for the surgical implants, and they are planning novel surgical techniques to implant this technology. And then we have people more like the neural engineer or the biomedical engineer that is the one that is combining this medical field with the technology. But we have roboticists working on the prosthetic itself, so with the robot. And also on the robot you need to put sensors, so there are people developing electronic skin and all this sensorized technology, sensing technology that is also needs to be very advanced. And now that there are very sophisticated small sensor that can detect an interaction, that is also for us very important, because if we have a detailed information of the interaction with object, we can send this maybe information back to the brain. And then there are people developing, as we mentioned before, small electrodes that are implanted in the brain, and that needs to be biocompatible. And so they they use materials that are more biocompatible, making these electrodes smaller with more channels. The electronics as well, like we're passing from having like a cable out, but now we maybe having something wireless, completely implantable, that is actually reducing the risk of infection or any damage. And miniaturize that, so making even like smaller, so people, electrical engineers and people working in electronics are there. So it's a it's a combination. And then there is all the software part and the algorithm part, with expert in AI, expert in real-time object programming. And so the team is very diverse and very multidisciplinary. And it's also the challenge, because sometimes if you don't know about the biological part, for example, that you are interacting, because your study are more on the electrical engineering part, sometimes it's challenging to think and to approach. So it's also the challenge is also that I feel like speak the same language and work on the same line for that. um so these are like the most many of the groups involved. But as we also just mentioned before, ultrasound or things like that. So I feel that the next generation will also combine other approaches that maybe are going beyond the electrical signal of the brain. We also mentioned at the beginning that the brain, the signal is also chemical, and there are many other things happening in our brain and so the usage of, for example, optogenetics or ultrasound, so other physical interaction with the brain, can maybe help um, to actually have even more information. One thing that is important, I feel that here we were at the research level in particular. Right now, the technology is available. It's available. It's still proof of concept, so not really available to everybody, but to people with disability. But most of these companies that they want to make a business on that, so they also are planning, or like they envision some usage in a able body person, like that we have a brain implant to interact with our computer and stuff like that. So more like for human augmentation. Also, like human augmentation is another thing that to me is still like not possible, because we struggle to help people to just give back some ability that is lost due to neurological. I feel very difficult right now to have like a technology that can give you like a more force, or like a better vision, or a better memory. There are some things maybe more possible, but still it's far. And also there is all the ethical question related to that as well. So also the field of regulation, neuro rights, neuroethics, that we don't need to underestimate the importance of that, grows in parallel with the development of technology. So we interact with experts in ethics and neuro rights, and to develop regulation for this technology. Because when we develop a technology like this that is new, there is not really a guidelines for regulation. So regulation are coming after, no? Because now we can do something that before was not possible. Okay, we need to have a regulation of that. So this is the reason why, in my opinion, in academia and in science at the research level, there is a lot of interaction between these two parts, compared, for example, for the industry.
Right. So the point of convergence, I think all tech stack, I think, is converging at this point in time, and that's beautiful. And I think not many people are paying attention, because I guess, when we are doing something, building something, we look at the tech in a very narrow lens. And I guess all of these tech stack is converging, and I mean, and the lines are getting blurred between, you said neurotech, ultrasound, optogenetics, AI, and so on and so forth. And the same is happening with VR. We started with VR, the lines are being blurred. We have got this XR and AI convergence, there's Web3 convergence, there's 5G, which kind of enables it. So I think the convergence it drives the utility and augmentation. Yes, I think these conversations are too early, but I think that we are in a cusp of sorts where gone are the days, the linear days. Everything is exponential. Because I think ChatGPT launched somewhere around November 2022. It's just 3+ years, but the kind of progress which has happened in the field is insane. And the kind of papers that's been written, my emails are always flooded. There's 10 people with 10 reports, and there's so many papers being written. So I see that we are racing, and possibly the timelines that we feel that okay, maybe we'll get to a product which is maybe like 10 years down the line, or maybe completely understand the brain, maybe which could be 100 years down the line. Maybe through these models that we are building, which is like people call AI co-scientists, which Google is building, Sakana is building, maybe these models will help us augment. In fact, Zyfra AI, they built a brain computer interface model, which is they're calling it Zuna BCI. It's like a 380 million foundation model for the brain, which does thought to text. What it does basically, it cleans up your messy data, EEG data, which is very, very noisy. It cleans it up. So I guess these field is going to combine, and then we're going to get to a product. Talking about a product, you said that at this point in time your lab is got like a POC out at this point in time. What would be the product, and would you be sharing that technology to a company to build it? What would be the roadmap, and what's the lab to market translation challenges over there? Because you kind of you talk about it quite a lot on your website. So would love to understand that.
That is absolutely important, because so we are a research lab at the university, and we develop we develop technology and algorithms up to the level of the proof of concepts. So like I feel at the university level, what you do is like you can do basic science research where actually you create knowledge, you study the brain, you're trying to explain something that you're observing experimentally. And then you have the innovation part related to the to more applied technology and the field of neuroengineering and biomedical engineering that I'm from is more on that side. Like try to create technology that can then become like an innovation that can maybe help people like and create a product. At the university level per se, this is like is bringing the technology up to a certain we call TRL level, but a certain like level of 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 uh, of the technology that reach the proof of concept. So we are the people that have like an idea, we develop a prototype for that, we test with the subject, we prove in few subjects that this is like actually functional and useful for the patients. And then we normally have two choices. One choice is to and there are, for example, students that decide to step out from the academia and from the university and decide to found their own. In that case, we'll call spin-off from the university. And this was the case for. We have some example of that, and one is Minerva, is one of the spin-off that started from the group and is now based in ETH Zurich doing. A neurostimulation device for pain, for people with the neuropathic pain, people with diabetes. That I think is an option for a student, and of course needs the support of the university. But the university can arrive up to a certain level. Then or like an industry partner will help to develop this technology, and or actually you have to build the company, your own company, and with a team of scientists, but also expert in business, and there are many challenges there because normally the people that develop the technology are for sure not the people that will bring the technology to the patients, because the knowledge that is needed to transfer a prototype in a product is huge. The fact to have like a team with expert of business with business part is totally missing. More in the education of maybe like an engineer or something. So we normally partner. We have like we create groups that are also including this like translational part, and we have also some part with the entrepreneurship, with our entrepreneurship fellowship for students that wants to bring their invention to a market. We collaborate with companies as well.
So I've got a question about the future, Giacomo, and where we're going with all of this. So you mentioned something that's personally very interesting to me, the idea of being able to control digital interfaces in a very sort of significant way using just the thoughts from our brain. Now, this for me is the final stage of virtual reality, because we've got the ability, we use a keyboard and mouse as a proxy now to try and control these machines, but being able to skip the middleman and go directly from this is what I'm thinking to this is the action on the computer or in the virtual world, whatever the case may be. Do you think that is a realistic prospect for the mass market? So thinking beyond ability versus disability, which is where the market is concentrating now, from what I understand. Do you think we'll see that in our lifetimes, for example, judging on the pace of progress in science in this area?
If you could.
Yeah, so this is exactly what they are thinking. Is one of the proposal of this company to like exactly make a real business connected to that. So not only people with a disability, as you mentioned, but people also to augment and give the possibility to interact with computers. Still, I don't know how many of us will decide to have a brain implant to control the computer. At least to me, it seems still maybe not a reason to do that. But they are also thinking about, augmenting some of your capability. Like, for example, let's imagine if you can have a better memory, or like expand your capability of computing through a brain implant, or even like connect ChatGPT with your your brain or something that you think about, and you expand your knowledge as well. But this is actually still a little bit difficult to imagine nowadays. Of course, it is still with the fact that the technology is still invasive and it needs a surgery, things like that. So I feel the adoption will be not super easy, and also the accessibility of this technology needs to be, but when we start to augment people, and then there will be some people around with more capability than others, and how you decide if you will have the access to this or not, and how the people without will there are still a lot of questions. So in my view, like in my small world, is more like trying to still work on the disability side with people. There are many diseases that still are without really a treatment that maybe this technology can support, and also the part about understanding the nervous system, because here we are really I make it like a very a clear example, at least in my field. So for many years, all the studies related to the sense of touch at this level of resolution have been done in monkeys. No, we mentioned before the monkey, the primate, the non-human primate is the closest in terms of our nervous system to us, and many of the technologies related to solve problems and disease and neurological disorders are tested first in monkey before arriving to us. But studying what you feel and what you perceive in an animal, it's difficult, no? Because you cannot ask the animal, "What do you feel? Tell me, what do you feel?" And so you need to infer and trying to understand what the animal is feeling, and you create some type of experimental paradigm. But what was incredibly cool is that the first time that we implant our participant with that, the human subject was immediately able to describe any particular feature of this sense of touch. No, it tells you, okay, what I'm feeling like something is touching my hand, is a kind of edge moving on the close to the tip of my finger. It's sharp or it's less sharp. So describe very well. So already this is giving us a lot of information about, okay, so if we stimulate this part of the brain in this way, the subject is feeling something like that. Or like we can evolve much faster than before in the animal, that you barely understood if the animal was feeling something or not. This is like a very simple example for my specific field, that is more about the sense artificial touch connected to BCI. But this is having this opportunity to have these pioneers, because I want to mention and highlight that the participants now that are present in this study are really the pioneers in the field, because without them, absolutely nothing will be possible. And they are actually the people that are not really benefit from this technology yet, no? Because this is still in development. So they are the people that will allow the next generation to have something that can maybe completely improve the quality of life. So, and they are fully dedicated to that. Our participants are working with us, are part of the team, are giving us the ideas to how to improve, because they can give the first person perspective as a person with a disability, what they need, what is needed, what is missing, and so they are really the pioneers. And thanks to them, we are also understanding a lot about the human brain.
Right. Giacomo, the last question to you, because I think we're running short on time. The future of healthcare with neuroprosthetics. When and how do you see that, becoming a reality?
Yes, this is it's very. I mean, this is a thing that is happening, and I feel this will be ready soon. I talked recently with the scientists in China, and he told me that that in some of the hospital already in China, they have in the hospital like a part for BCI and neuroprosthetic, like a department or something, that where the neurologist, for example, if the neurologist doesn't have any treatment anymore that can give to these patients, they will send this person to the BCI facility and start to use a more research-based approach with BCI neuroprosthetics to recover. No, so the is like now there is even there is the way the time where we will have like a part in the hospital dedicated to that. But we can think also at the technology like cochlear implant or deep brain stimulation for tremor and Parkinson. These are now neuroprosthetics that are used by millions of people, and they don't. If you think about exactly kids with hearing implants, and so they actually are in the are going around since many years. So this is like, I feel that the field is very expanding. This is a reality that the technology will be literally part of us, and is becoming part of us already. So I think this is become like a very reality soon.
Right. Giacomo, really, really appreciate you taking time and being part of the podcast. Jeremy, really, really appreciate you being the co-host. And I think we're sitting in
My
such
pleasure.
a fantastic point of time. We're at the cusp of maybe possibly in another 50 years or maybe sooner, maybe possibly understanding the entire human brain, the magic, the two-pronged brain, which, creates everything that we see, if we are able to understand that, I'm sure there's millions in the world who are kind of suffering today, amputees, paralytic patients, ALS, Down syndrome, the list kind of goes on and on. We will not be able to just maybe possibly, take those, problems away, but also the other side, maybe understand the brain better, and someday possibly go for the holy grail, build machines which resembles us, general purpose machines, and if we are managed to do that and manage to do that in a way which is helpful for the society and the larger good, what a beautiful world would that be. Please keep on doing the great work that you're doing. Thank you, Jeremy. Thank you, Giacomo. And to my listeners, if you like what you see in here, then please press the subscribe button. Until next time, see you guys. Thank you. Really appreciate this. Yeah? Thank you.